Good morning. We're going to finish up chapter on acids, bases, and equilibrium. Got through the first half. Now we're going to work on the second half that has to do mainly with calculations and numbers. So let's look at we'll start by talking about in this image the dissociation of water. So water does this thing called self-ionization, meaning it ionizes itself. So if you have just pure water, all right, a water molecule in a water molecule will actually react with itself because remember, water is amphoteric, so it can be an acid or a base. So one of the waters will take a hydrogen from the other water, and what you'll be left with is a small concentration of H3O plus and a small concentration of OH minus. So you've got some acid stuff and some base stuff. But this is a equilibrium equation. So these two things will then, redistribute the hydrogen so that you go back to the water. And if we're dealing with a neutral solution, so a solution that we say has a pH of 7, the concentration of the acidic thing and the concentration of the basic thing are exactly equal to each other. So right here, you can see here's my acid, here's my base. Those two values will equal each other, okay? If we're in an acidic setting, the acid or the hydronium ion, the H3O plus, is going to be much higher in concentration than the OH, right? The H3O plus is sort of winning out. There's more of it. So we can't neutralize all the H3O plus with what OH we have. If we're in a basic situation, the H3O plus concentration is much lower than the OH minus, or we have a lot more base. So here is sort of a picture of the self-ionization of water. So we've got one water acting as the donor, one water acting as the base, and then we end up with the hydronium ion and the OH. And you can see this is one, whichever water it happens to be, will be behaving as the acid with its conjugate base. And here we've got a water that's acting as a base with its conjugate acid. There is an equilibrium that is reached between this forward and this backward. So there is a specific concentration of these two things at a given temperature. In pure water, okay, so this is not salt water, doesn't have anything else in it, it's just H2O molecules. If you're at 25 degrees Celsius, you reach this very specific concentration. Both the H3O plus and the OH minus will have a concentration of 1.0 times 10 to the negative 7. Okay, so it's a very small concentration, right? We'd have to move the decimal out 7 spots. But that is constant. If you have, pure water at 25 degrees Celsius here in the United States, if you were to run the same experiment and have pure water at 25 degrees Celsius in India, you would get these similar concentrations. Now, if I take the concentration of, and the concentration of the H3O plus and the concentration of the OH minus, they equal each other in pure water. If I take those two values and I multiply them together, I get what's known as the Kw constant. Okay? And Kw is always going to equal 1.0 times 10 to the negative 14. Now, this little nifty equation here, this little nifty thing right here, Kw, which equals 1.0 times 10 to the negative 14, this value is true for all solutions. These two components, the H3O plus and the OH minus, those can change, okay? So this equation right here, you can use for really any solution to determine how much H3O plus, how much acid you have, or how much OH you have. When you see these things written with brackets, The bracket is indicating that this is a concentration, okay? So what is the concentration? So your values, usually when things are written in brackets, is going to be big M, molarity. We're not talking about grams here. We're talking about a concentration. So the ion product, or the Kw constant, is 1.0 times 10 to the negative 14. This is true for all of our solutions. So if we're in a solution where H3O plus equals OH minus, they're equal, it's neutral. If we have more H3O plus and less OH, it's acidic. If we have more OH and a greater amount of H3O plus, we're in a basic solution. So super nifty equation, because what if I said, hey, I have a solution and it contains like 6.02 molarity of HCl. And I want to know how much base it has. I could calculate how much base is in this solution because I know how much H plus is in the solution. So if I'm given H3O plus, or something about the concentration of the acid, I can figure out the OH concentration. Actually, I would use this equation here. If I know this value, I can plug it in and find the OH minus. Because what's the Kw constant? This thing is always 1.0 times 10 to the negative 14. So I'm going to make a little visual. I call it like the pH box. And we're going to fill it in with some of these equations. No, you don't want email. Oh, okay. Okay, so I want you to put H3O plus concentration in the upper left-hand corner. In the upper right-hand corner, I want you to put OH minus concentration. So this is talking about something, the concentration of an acidic component. This is talking about the concentration of a basic component. In this lower left-hand corner, I want you to write pH. And we'll get back to that a little bit later. And then in the lower right-hand corner, I want you to write POH. So let's make that. No, I don't want P. Oh, okay. So right now we can actually go between these two things. If I gave you one of these, you could calculate the other one because we know the Kw constant. So let's fill in an arrow or a little pathway. And let's put the equation in here that Kw will always equal whatever the H3O plus concentration is times the OH minus concentration. And this whole thing, again, let's write the Kw constant, which is 1.0 times 10 to the negative 14. You can rearrange these two things to isolate, right? If I want to solve for H3O plus, I have to divide the constant by OH. If I want to solve for OH, I need to divide the constant by H3O plus. So let's do a couple of those. We can check that limb off. We've already sort of talked about this, but when the two concentrations equal each other, it's a neutral solution. If the H3O plus is exceeding the OH minus, it's winning, there's going to be more acid in solution, so it'll be an acidic solution. If there's more OH, the basic quality or properties are winning out, so it'll be a basic solution. All right, let's do an equation or a practice problem. So when calculating one of these, state the givens, what you need, use the KW equation to go for it. So I've got this here. What is the H3O plus concentration of a solution if the OH concentration is 5.0 times 10 to the negative 8? You're going to want to get comfortable with negative exponents and seeing negative exponents when you're doing all these equations, okay? That is going to be sort of the general presentation, because we're not dealing with really high concentrations here. Oh, come on, pen. Okay, so we're given OH. We want to find H3O plus. We are given OH, want to find the H3O plus. I know that I'm going to use the KW constant because that's the only way to hop between those two. So here's my KW equation. KW equals H3O plus and the OH minus to give me 1.0 times 10 to the negative 14. Now I want to rearrange this equation because I want to get H3O plus by itself, right? I want this thing solo. So I need to divide by OH and divide by OH. That's what you have going on here. So this will be the sort of the final isolated equation set up for you. So H3O plus, what we're looking for, is going to equal our KW constant, 1.0 times 10 to the negative 14th, divided by the OH. What is the OH concentration? That was what was given to us. So I want you to physically plug this into your calculator because people tend to get wrong answers because they're not putting things in equations or they're not using the EE button. They're not using parentheses or EE buttons. So in this one, we're going to do KW and we're going to actually divide it by that 5.0 times 10 to the negative 8. Now, if I was plugging this in the calculator, I would use the EE. So I would go 1 EE negative 14 divided by 5 EE negative 8. That's how I would approach it, as the fastest way. The EE being a button that you have available for you. So just,
I get a syntax error when I hit EE.
you're getting a syntax error?
Yeah, so I have a button that says EE, but I have to hit it. I have to hit it twice to get it.
No, you just hit it once.
Oh, but it only has one E when I hit it once. Okay.
Yeah, that's fine. Yeah. So you should get something like 2.0 times 10 to the negative 7th. It is extremely important that your exponent value is correct. If you're like, oh, I got 2.0 times 10 to the negative 8th, that was close enough, right? No, we definitely want to be smack dab on that right exponent, because that tells us something about how acidic or basic it is. Now, if we were to determine, okay, we know the H3O plus concentration and we know the OH minus concentration, and I just want to know, is this solution acidic or basic? Well, let's look at the concentration of each. Here's my acid thing. I'll even write the word acid next to it. Here's my base thing. Right, these are both floating around in solution. Which one is winning? Which one is a higher concentration? The acid is a higher concentration. Remember, these are negative values. So this is 1 decimal place smaller than this one. All right, so the base is lower, the acid is higher, so the solution would be acidic. And that's how you use the KW constant. I want you to go ahead and do this one. So if lemon juice has an H3O plus concentration of 2.0 times 10 to the negative 3, I want you to tell me what the OH solution or concentration is. It gives you a couple answers, but just go ahead and solve it like you don't have those there and then check after. so we're given H3O plus. We want to solve for OH. So first we need to, write out our KW constant and then isolate appropriately. So the only difference from the last problem is that instead of solving for H0 plus, we're solving for OH. So my OH is on the left side. It will equal the KW constant divided by whatever the H0 plus concentration is. So Kappa. Cecilia's here. All right. So we take our KW constant, we divide it by that 2.0 times 10 to the negative 3, and we should end up with 5.0 times 10 to the negative 12. We already knew that the solution was acidic because it said, well, we didn't know, but I mean, lemon juice is going to be acidic. But let's just prove it, right? Where is my acid concentration? Here's the acid thing. Where's my base? Right here's the base. Which one is bigger? Oh, this is way bigger than this one, right? This is a super teeny tiny number. So our solution is definitely going to be an acidic thing. So you'll want to be able to calculate for H0 pluses and OH minuses, and you want to be able to tell me if the solution is acidic, basic, or neutral. Let's work on filling in a couple other limbs on that square. So the pH scale, which you may be familiar with, the pH scale is something that's used to describe how acidic a solution is. Look in the name of it. So pH. When it's saying H, it's referring to the hydrogens, right? Or the H3O plus, because remember these two things are interchangeable, right? So pH is talking about how acidic, how much acid, how much H3O plus we have floating around in solution. Cranberry juice over here is a very acidic material. It's got a pH of 2.9. On the pH scale, the lower the number, the higher the acidic component. So the pH scale runs from 0 to 14. 7 is a neutral pH, so right in the middle is where our pure water is. If the number is less than 7, we're acidic. If the number is greater than 7, we are basic. Another way to sort of think about that from the previous slides, remember, if your H3O plus concentration is greater than that middle part, right? Because the neutral solution cutoff point is 1 times 10 to the negative 7. If H3O plus is greater than that, it's acidic. If H3O plus has a lower concentration than that, it is a basic solution. So the pH of a solution is commonly measured using, we have pH meters in labs, and then there's also indicator paper, pH paper. And then you compare the pH paper, you stick it in the solution and you compare the pH paper to some sort of chart that has all the different color indicators. Here's just an electronic pH reader. Here is the pH paper, and then here they're using cabbage juice because cabbage juice has anthocyanins in it, which will change color depending on what the pH is. You can measure pH that way too. That's definitely, obviously, like the most cumbersome. Some things on the pH scale. So let's go to that middle area. Come on. This pen is driving me crazy. The middle area, pure water is neutral. Drinking water, what you get out of your faucet, is usually generally slightly basic. Has a pH of like 7.2. If we go into lower pHs, so a lot of the things that we eat are lower pH or slightly acidic. All right, so milk is 6.4, coffee is 5, tomatoes, apple juice, carbonated beverages, lemon juice, all these things, the acidic things, we tend to, not everything that's acidic we ingest, but most of the things we ingest are acidic. If you look over here, our stomach, gastric juice is sitting at about a 1.6, so very, very acidic. So if you've ever had like heartburn, the reason that it hurts so bad is because the acidic juices of your stomach are literally coming up into your esophagus. And your stomach has a lining in it that makes it so that you can sit comfortably with acidic juice in it. But your esophagus doesn't have that same coating, so that's why it gives it that sort of burning quality to it. If your stomach acid becomes too acidic or you're too stressed, this acidic juice can start to burn holes in the lining of your stomach. What about on the higher end of our pH scale? So a lot of things that we clean with are basic. You can see they've got detergent, seawater is basic, milk of magnesia, ammonia, bleach, sodium hydroxide solutions, all these sort of basic things. So this says identify these as acidic, basic, or neutral. HCl with a pH of 1.5. That's definitely acidic. Any time you have a pH below 7, it's acidic. Pancreatic fluid. So pancreatic fluid has an H3O plus concentration of 1.0 times 10 to the negative 8. Now remember, the cutoff point is 1.0 times 10 to the negative 7. When you have one of them equaling that, you can assume a neutral solution. This concentration is less than the sort of middle or cutoff point. If it's less than, it means we have less of the H3O plus than we do of the OH minus. The OH minus is winning out here. So this would be basic. So we've got acidic, this is definitely basic. Sprite, pH of 3, that's acidic. pH of 7, that is neutral. OH concentration of 3 times 10 to the negative 7. Is that greater than or less than your cutoff point? It's less than that middle cutoff point, right? 3 times 10 to the negative 10th is less than our 1.0 times 10 to the negative 7. So that means the OH is losing or the acid has to be winning. So this is acidic. And then this last one here, we've got H3O plus concentration. This is smaller than our neutral cutoff point. So this is in the minority or is losing the battle with the whatever the OH happens to be. So we will say that this is basic. So how does the pH scale relate to some of these other numbers that we've been looking at? It's not just like some arbitrary number. It actually is talking about the specific concentration of your acid in solution. It's a logarithmic scale. So here is your equation. It says that the pH is going to equal the negative log of whatever your H3O plus concentration is, or your acidic concentration. Log is the opposite of 10 to the, so you know how like addition, the opposite is subtraction, multiplication, the opposite is division, right? That's how you undo it in an equation. Well, if I have an exponent, like I do in a lot of these numbers, like this, to undo this 10 to the, it's log. That's where that's coming from. So let's fill this in to our chart. And we're going to put 2 arrows because it is important which direction we're going in. We know this relationship over here now. So I'm going to put 1 arrow going down and 1 arrow going up. If I know this concentration, I can get the pH. pH equals the negative log of the H3O plus. I'm going to turn this equation inside out. Actually, I'll just show you for my math people who like to derive things. So what is the opposite of this equation? If I have pH equals the negative log of the H3O plus concentration. If I want to get H3O plus isolated instead of pH isolated, I need to undo or invert the equation. So the first thing I'm going to do is move the negative over. So negative pH equals the log of H3O plus. Now I want to undo log. I said the opposite of log is a 10 to the. So I'm going to put this 10 and this in the exponent. I'm going to put a base 10 and this will be in the exponent. This and this will cancel. And I'll be left with 10 to the negative pH is equal to my H3O plus concentration. So if you're wondering where I got the other one from, that's how I derive it. So let's actually fill that in on the other arrow. So if we're going, if we know pH and we want to get H3O plus, H3O plus is going to equal 10 to the negative pH. So it is important which one you use going in which direction. Let's look at a couple examples. So here it says, calculate the pH if you know that the H3O plus concentration is 1.0 times 10 to the negative 2. So I want you to plug this into your calculator because I want you to get comfortable with where the log button is and stuff. So I know pH equals the negative log of this H3O plus concentration. So I'm literally just going to take that H3O plus concentration, this thing here, and insert it into my equation. So when plugging this into your calculator, if you have a scientific calculator, just plug it in the way it looks like this. If you're using your cell phone, you have to actually plug the number in first and then hit the log button. And where is the log? You have to turn your calculator on the side to get expanded functions. So I've got what, 1.0 EE to the negative 2. I need to take the log of it. So first on my cell phone, again, first I plug this in, then I hit the log button, and then I'll reverse the sign out because it's a negative. So we get a pH of 2. Is that acidic? Oh yeah, definitely acidic. Do you see how it's a 2 in the exponent here? And then it happens to be a 2 over here. That is a direct relationship. To determine the number of significant figures, the 2 again, yeah, so the 2 is coming from the exponent here, and then this number, whatever this is, will give you the decimal places. So really go with however many sig figs this is here, that will kind of be however many decimal places you'll have. I'm not going to be a huge stickler about sig figs on this. Okay, so because pH is a logarithmic scale, a change of 1 pH unit corresponds actually to a 10-fold increase or a 10-fold decrease. So a pH of 2 has an exponent of 10 to the negative 2, right? But a pH of 3 has an exponent of 10 to the negative 3. That's a full, exponential factor down. pH of 4 is 10 to the negative 4. So when you're dropping pH by 2, 3, 4, you're dropping by factors of 10, not by factors of 1. So let's do a calculation. All right, aspirin, which has acetylsalicylic acid, was the first non-steroidal anti-inflammatory to alleviate pain of fever, and it is awesome. If a solution of aspirin has an H3O plus concentration of 1.7 times 10 to the negative 3, I want you to tell me what the pH is. So go ahead and calculate pH from that given H3O plus concentration. Okay, so when plugging this in, pH should equal the negative log of our value of 1.7 times 10 to the negative 3. Use your EE or your exponent button to calculate it. 2.7695 is what your calculator should display. The 3 is the exact value, so that's the 2. And then we have 2 sig figs or 2 decimals. So we would go 2.77 as our pH. Does that make sense with aspirin being acidic? Yeah, it does. Okay, real quick, calculate this one. The pH of solution with H3O plus of 4.0 times 10 to the negative 5. Give you just 40 seconds. All right, so we're gonna just literally plug that value into the same equation, negative log. This time we'll have 4.0 times 10 to the negative 5th. So exponent y or value wise, your calculator should have put out 4.39794. Again, the exact value, the 5 is corresponding to that 4 value. So that's our exact, and then we get 2 sig figs. So 4.40 would be our sig fig. It's acidic. Calculating H3O plus from pH. So this is the inverse of the equation. You should already have that written down. The H3O plus or acidic concentration is equal to 10 to the negative pH. So determine the H3O plus concentrations for each of these pHs. So I want you to do that on your own, knowing that again, H3O plus is equal to 10 to the negative pH. You have pH. Okay, so when plugging it in, you should get, let's see, these are. So for A, when you've got the 3, you say 10 to the negative 3, and really 10 to the negative 3 is this thing right here, 1 times 10 to the negative 3. That's pretty straightforward. Again, this value is this value here. You're going to want to get comfortable again writing things in scientific notation like this, or being able to identify it. The other one, I had 3.42. When we plug it into our calculator, we get something like 3.8 times 10 to the negative 4. Again, your calculator may have given you something like 0.00038. with a bunch of exponent or decimals, you just want to use the 2 sig figs and you want to write it in scientific notation. So when looking at our H3O plus concentration and our pH and our OH, right, as we move into acidic domain, our pH number goes down, our H3O plus concentration goes up, our OH concentration will decrease, right? Then as we go through a basic, our number increases for pH, our concentration of the acid or the H3O plus will decrease, and our concentration of the base will increase. So I want to finish up that chart. There's another thing called POH. POH is sort of like pH, but it's talking about the OH concentration. The equations are the same, except they're relating these two things. Okay, so whereas the pH is equal to the negative log of the H3O plus, POH is equal to the negative log of specifically the OH concentration. And then in the other direction, if we have if we want to find OH concentration, OH is going to equal 10 to the negative POH. So these equations are similar. We're just using, here we're using pH and H3O plus. Here we're using POH and OH. One more thing that we can fill in is this right here. In this area, pH plus POH always equals 14. So if you have a pH of 6, right, pH equals 6, your POH will equal 14 minus 6 or 8. That's an easy one to flip back and forth. So now, you know, I could give you something like the H3O plus concentration and you could solve for the POH. Or I could give you the pH and you could solve for the OH concentration by going through this flow chart. You can't go across diagonals. You can only go on the square on the outside. So just to make sure we get through everything today, I'm going to keep moving forward here. So reactions of acids and bases. We've kind of covered some of this already, but over here, okay, gastric acid in your stomach is made up of HCl and is produced in the cells of your stomach. The reason that our stomachs are acidic is because it helps to kill the bacteria in our food so we don't get sick. Acids will react with, they do a couple things consistently. So if an acid comes into contact with a metal, it produces salt and hydrogen gas. If an acid comes into contact with a base, it will produce salt and water. And if an acid comes into contact with a bicarbonate or a carbonate, that's the CO3 or the HCO3, it will produce carbon dioxide gas. So here's an example of acid combined with a couple different metals, say potassium. So I've got hydrochloric acid, it's combining with potassium. What happens here is a single displacement reaction, or the potassium boots the hydrogen off. It combines with the chlorine to form a salt and then releases hydrogen gas. Doesn't really matter what metal it is, as long as it's one of these metals. There's not every metal does this. It just has to be one of the metals that will react with an acid, but it follows a similar situation where the metal comes in, it steals the non-metal from the acid and it boots the hydrogen. This is why metals will dissolve in acid, because the metal is combining with the non-metal of the acid to produce an aqueous material, as opposed to it being a solid material, and then it can dissolve in solution. Keep moving there. Okay, if an acid combines with a carbonate, or a hydrogen carbonate bicarbonate, your products will be carbon dioxide, salt, and water. So here I've got an acid. It's combining with calcium carbonate. I know that one of the products has to be CO2. So I'm going to write CO2. The remaining things, we will have water and then a salt with whatever's left over. So whatever brought the carbonate, that metal will combine with the non-metal from the acid. You can see that there's sort of a consistency here as well, right? I've got an acid here and a bicarbonate. The products are going to be carbon dioxide, water, and then a salt based off of whatever was getting, bringing the bicarbonate and the non-metal from the acid. So if we were to write a balanced equation for these, we've got magnesium carbonate combining with hydrobromic acid and hydrochloric acid combining with sodium bicarbonate. As far as what the products would be, well, I know for this first one, I would need to have CO2 because it's a carbonate. I know that I'd need to have water. And then the last thing would be to combine my salt. The salt, again, is going to be the metal that's sitting with the carbonate and the non-metal in the acid, so magnesium bromide. As far as what's happening here, we would have CO2, we would have water, and then we would combine the metal and the non-metal to form a salt. So there is our balanced salt, magnesium bromide. There's the CO2 and the H2O. Here we've got sodium chloride. There we've got CO2 and H2O. So you can consistently expect that those would be the types of products if you have a bicarbonate with an acid. Acids and hydroxides, or an acid combined with a base. This is known as a neutralization reaction. Anytime you have an acid that combines with a base in this way, you're going to produce a salt and water. This is a double displacement reaction. We have already gone over this, but the H combines with the OH to produce the water, and the Na and the Cl combine to form the salt. All right, so I want you to write the balanced equation for magnesium hydroxide and nitric acid. So this problem sort of asks you to remember your nomenclature. Magnesium hydroxide, you have to know what nitric acid is. So you'd write magnesium hydroxide and nitric acid. We know anytime it's a neutralization reaction, these are your products, water and a salt. So the water is going to be coming from the H, the salt, and the OH. The salt will be coming from the Mg and the NO3. So this will be Mg, NO3, 2. When you're balancing this, they put it in as just the word like generic salt because this balancing system always applies for everything, doesn't matter what the salt is, but you'll balance the H's in the acid with the OH's in the base. So here I've got 2 OH's. So I need to have 2 H's over here. So I put a 2 in front of the acid. I need 2 acids to balance every one base. Then you need to balance the water with the H's and the OH's. So if I've got 2 OH's here and 2 H's here, I need to have 2 waters here. And then you just write the salt in. All right, I'm gonna keep moving forward. All right, yep, we're gonna do it. Okay, so we are gonna do a little bit of solution stoichiometry for these titrations. I wanna get through this before the end of class, which we should be able to. You know what? No, we're not going to, no. Okay, you are welcome. We are not doing solution stoichiometry or titration problems, all right? So I will pull that, let me make a note. I will pull that off of your next test. Okay, we're just not going to do it. Let me make a note. No. Okay, because honestly, I think it's more work than it's worth, and we've got other stuff that we're going to want to go through for the semester. So by solution stoichiometry. I will talk about the concepts of it though. So an acid-base titration is an experiment where you have a known amount of one material, of an acid or a base, and you're trying to figure out the concentration of the opposite. So if I know the concentration of the acid, I'm trying to figure out the concentration of the base. The way that I do that is I try and reach what's known as the equivalence point or the end point, which is where the amount of acid and the amount of base equal each other. When they equal each other, if I put an indicator in this water, usually phenolphthalein, which turns it purple, or I'm sorry, pink, it'll turn this light pink color, and I know that the two have equaled each other. So here's our phenolphthalein indicator. As I add acid or base, depending on what is in the tube, it will change a pink color. Once we've hit the neutralization point, or when all the acid and all the base are neutralized, it'll give me this faint pink color like this. This is the end point. At the end point, conceptually, the moles of the base are equal to the moles of the acid. If I was to take this pH in here, it would be a pH of 7. Now I know how much of one thing I had to use to neutralize the other thing. If I know how much of one thing I needed to neutralize the other thing, I can do some fun calculations to figure out the unknown. We aren't going to do that. So we're just going to bypass all of this. All right. I do want to talk about buffers though. So what is a buffer solution? Something in my nose. Something in the air today. Okay, so a buffer solution is put into a material to help maintain the pH, meaning that if we add small amounts of acid or base, the pH won't change. It doesn't necessarily mean that it keeps it at a pH of 7. It just means that it keeps it at whatever its original pH is. In this case, they do have a pH of 7. It's a buffer solution. If I was to add more acid, it would just slightly change pH, but it wouldn't dramatically drop into the acidic range. If I was to add base, it would maybe just slightly increase, but it's not going to like fall into the base range. So if we didn't have a buffer, this is what would happen. If I just had like neutral water, if I add acid, it's going to slide into the lower pHs very, very fast. If I added base, it would slide into the basic pH very quickly. The buffer prevents that huge swing in pH. And so what is happening in a buffer solution? Buffer solutions work because they resist change in pH from either additional acids or bases. They're super important in the body. We have lots of buffer solutions in our body to help maintain specific pHs depending on what the system is. One example is our blood. Our blood is a giant buffer solution that has a pH of 7.4. If we were to add too much, or if we were to add, acid or base to the blood system in some way, it would sort of help balance that out. If we shift our pH in our blood too much, then yeah, it can have issues with oxygen intake. So how to make a buffer solution? Astrid, are the buffers usually good for both acids and bases, or do they need to be acid buffers and basic buffers? No, you only need to have one quote unquote buffer, okay? The buffer will take either additional additions of acid or base, and we'll look at what is going on here. So this is a good example of a buffer solution. It's got an acid-base conjugate pair, okay? So it's usually some sort of weak acid and a conjugate base. and sometimes they call it the salt of the conjugate base, because this has a charge on it. This has a charge on it. So real easily, instead of writing it like this, I could write it as, NaC2H3O2, like a salt kind of stuck itself on top of that. Or I'm sorry, a metal stuck itself on top of that to make a salt. You have equal concentrations of the weak acid and its salt. Now, the reason it needs to be weak is because you have to have this and this existing at the same time, right? If it's a strong acid, everything dissociates and you have no more of the weak acid left. We want something where some of the weak acid is floating around and some of its conjugate base is floating around. If I have both in solution, and this kind of ties back to Astrid's question, the weak acid, what is it going to eat up? Additional base. The weak or the conjugate base, what is it going to eat up? Any additional acid. So we need both of those in the solution simultaneously. So in our buffer solution this is acetic acid and then sodium acetate, the salt will produce, this guy here will produce the conjugate base, and then this thing is just sort of floating around as a spectator. We have a large quantity of our weak acetic acid, and we'll have a large amount of our conjugate base. If I was to look at this equation as a Bronsted-Lowry, these two things would pair up, and these two things would pair up, right? This is the acid. This is the conjugate base. It has to be in this sort of pairing to make it a buffer solution. So let's say I've got my acetic acid that's floating around in solution and I add base. What gets produced? Well, what will get produced is some of the weak acid and water, which will help to neutralize the addition of the base. What if instead of adding a base, like I did here, I add acid? Well, the acetic acid, or the acetate ion rather, the salt that's present, will take the hydrogen from the acid and turn it into the acetic acid and water. So these two things are happening simultaneously. The acetic acid is neutralizing additional base. The acetate ion, or the conjugate base, is neutralizing any additional acid. So here we've got our center point. This is where, our two values are equal to each other. If I add acid, I'll increase the amount of weak acid. If I add base, I'll increase the amount of conjugate base, but just slightly, not a lot. It isn't going to be a huge swing. So if we wanted to look at these things and determine which of these is a correct buffer solution. Remember, a buffer solution, it has to be a weak acid. Okay, so one of the things is a weak acid, and it has to be with its conjugate base, or its conjugate salt base, because it has like a sodium on it or something. So let's look at this first one. Hydrochloric acid, is that a weak acid? No, weak acids do not work. And this, yeah, we don't like this. No. Why? Because it's a strong acid. Think about if you put a strong acid in solution like HCl, it's just all going to become H plus and Cl minus. There is no moving back and forth. So both of them don't exist simultaneously. So all this thing can do is eat up base. It's not going to be able to eat up any acid because it is itself only an acid. So we don't like that first one. And I just erased everything. Come on. And it's not going to let me do it. That's okay. So we don't like this one because it's a strong acid. This second one. Okay, so this thing here is an acid. Is it a weak acid? Yes, this thing is in fact a weak acid. We like that, okay? So this part is good. What's happening here? We need it to be its conjugate base or its conjugate salt base. How do you get a conjugate base? You got to strip off a hydrogen. Have we stripped off a hydrogen? Here we had 2 hydrogens, here we have 1 hydrogen. I like that. And there's a sodium sitting in front of it. The sodium is just allowing this to get delivered into the system, okay? So these things are both looking good. I think that would be a very good buffer solution. Let's look at this next one. Okay, this here, is this a weak acid? Yes, it is a weak acid, so I like that. Is this its conjugate base? No, this doesn't correlate to this at all. That makes no sense at all. What would be inappropriate? So this is definitely not a buffer solution, but what would be a more appropriate thing would be like NaH2PO4. Okay, we're down a hydrogen, and then we have some sort of salt, metal, making it a salt. This would work. This definitely doesn't work. Okay, so we're not a base here, or we're not a buffer here. Let's look at that last guy. What do you think about that last guy? Is this a weak acid? It is, so we like that. Is this its conjugate salt base? It is. It's the original acid minus the hydrogen replaced with some sort of metal. So I like that. Those two, B and D, are great buffer solutions. All right, so we are done with that. So your test will be on Sunday, Monday. It will not include titration. You may see titration in solution stoichiometry on your homework, and I'm just going to let you battle through that, but you will not be tested on it formally. Okay. So yeah, if you have any specific questions on what we've gone over, let me know. If you have any personal questions, you can stay around and we can meet individually. Otherwise, have a really nice weekend. Enjoy this like fabulous weather we've been having. I think we get another couple days of it in here. And I'll see y'all next week.
So I have on my calculator, I don't have an EE button.
What are you using?
It's just the TI 30XS Multiview. It's just a very simple calculator.
Can you show me this? Can you show it to me on your screen?
Yeah.
Cool.
So it's just.
Oh, you should have one somewhere. Is it like
So
on the, is it the second?
So I
is
haven't.
it yellow sitting somewhere?
No, I was, while you were talking, I was trying to look over it. I do have an option to do